So we've covered in lectures all the theory, the kind of general equations, the descriptions of the properties or attributes of Kriging for making spatial estimates. And so, as with most of the things we cover in geostatistics, it makes a lot of sense to get a little bit of hands-on practice. But when we get to something like Kriging, we set up a spreadsheet and we looked at making individual estimates. It's good to take a look at how it behaves when you try to build entire models with Kriging, where you have estimates at all possible locations within some type of area of interest. And we want to observe and see how Kriging behaves and look at estimation variance. So to do that, we better start using some real software to do that. Fortunately, in R, we have the GStat package that was developed by Pyrcz, which is actually pretty useful. It works pretty well. And we can use this in order to build some Kriging, and later we'll do simulation maps with it. Now, we could run through Rstudio, and I could show it to you in Rstudio, but I find the documentation of Jupyter Notebook is really, really good. We can, of course, use really nice markdown descriptors and so forth. Now, of course, we could do the same thing within R. We can do R Markdown and so forth. And I actually have, I think I produced one of these and put it on GitHub. But for now, we'll just together go through the Jupyter Notebook version of this. Now, I already have a short lecture where I show a short description of how to install the R kernel. Once you've done that, you're free to now use Jupyter Notebook with R code. And so the next step is we're going to want to install the GStat package. That's not standard. It's not built into Anaconda, so we have to install it on our own. You can use the install packages GStat command. I found that I ran into errors. Exactly where's the repository, all the parameters for the install wasn't set. So I went online and I found some really good help where there was this set of parameters that were set, specifically where's the repository and so forth, or where is it being downloaded from. And so if you uncomment these commands right here, the first time you run it, for me it worked, it was able to install GStat. So we have GStat installed. Moving forward, assuming that we have that, we can of course run that block of code in order to install all of our libraries that we need to work with, the packages that we want to work with. Dog just came into my office and is now on her way out the other side. All right, so the next thing is that since we're working with space and we're making estimates in space, we're going to need to know what locations we're estimating at. And so this is the two-dimensional regular grid that we're going to work with. It has the number of nodes in the X direction, the Y direction, and the minimum cell centroid and the size of the cells. Now, anyone who's ever worked with GSLib, which is the standard geostatistical library, will recognize this parameter as exactly the way that grids are specified in GSLib. It is a grid system in which we take the bottom cell. This is going to be the first cell within the grid scheme. The X min, Y min is the coordinate of the centroid of that cell. And then the cells are going to index first IX from 1 to NX here. And then we will increment up one cell to the next one. And we will go across from IX equal 1 to NX. And we increment up again. And the last cell in 2D will be this cell right here. So this is the general approach for geostatistical library, GSLib type cells. I think it's called the GeoDAS format. I'll have to look that up. But if we, it is the GeoDAS. I hope I've got that right format. Now we're going to do some varogram calculation. We're going to have varograms, but we won't focus on the varograms. I think, in fact, we just assume varograms in this workflow. But when we're doing varogram calculations, we may use them with normal score properties. If we're doing simulation, we want to work with things in Gaussian space. The normal score transform transforms the data values to Gaussian distributed with a zero mean and a 1 for standard deviation or variance, the same. And that is the standard normal distribution that we'd want to work with if we're working in Gaussian space. In addition, I made this little function here. I should give credit to Ashton Shortridge for writing this n-score transform. Really nice and very convenient to work with. I borrowed that from, I think, Stack Overflow or someplace like that. And then I wrote a little program, add chord, that's going to make a two-dimensional data frame with all the centroids of all the cells that we're going to estimate at, based on the geostatistical library convention for the gridding scheme. NX, X min, X size, Y, NY, Y min, and Y size. And that'll give you a data frame of all these centroids so that then we're able to feed that into the Kriging program and tell it that we want to estimate at those locations. The next thing we'll need to do, like always, is we'll set the current working directory. We'll have our data files there. We'll be able to load them in, everything we write out. If we do write things out, we'll go back to that directory. I like doing that because then I just never have to hunt down files. If you're working with Macintosh, of course, you'll have a little bit of a different convention of how to specify the directory, and you could check that out. If you're really stuck, go into Rstudio and use in the GUI, set the working directory. You can do that in the bottom right of the GUI, and it will give you the command to set the directory. You can navigate to the directory on Mac, set the directory, and you'll see exactly the code you need to do that. Once we set the directory, you can load in the data file. The data file is available at GitHub Geostats Guy Geodatasets. It's a 200-well data set with multiple variables. They have interesting correlations and so forth. It includes facies, facies assignment, porosity, permeability, and acoustic impedance. So these are all interesting spatial multivariate data set to work with that I put together. It's synthetic, but it has some really nice features to it. Once we loaded it, we load it into my data. It's a data frame. And so we can use the head command on the data frame to get the first 6 rows of the data along with a nice formatted table with the names of the categories, the names of the individual features that we're going to work with. And so this is very useful to get a quick preview. We'll do a little bit of data preparation and cleaning. We're just going to check the data, make sure everything's okay. The first thing we have to do is, if we do a class myData, it'll tell us that myData is just a data frame. But in order to do any geostats with that, we need to convert it into a spatial point data frame. And what's really cool about that is all we have to do to convert a data frame to spatial point data frame is simply specify its X and Y coordinates, or spatial coordinates of any type. And so we can say coordinates myData, my previous data frame, equal X plus Y. That's communicating that this in fact is a spatial point data frame, and the X and Y, if you look right here, X and Y are the name of 2 of the features in the data frame, are now going to be known not just as regular old features, but as the coordinates, the locations in space. Now if you do a summary of my data, it'll tell you it's now a spatial point data frame. So it's converted it. It's kind of cool because the summary will tell you the range in X, the range in Y. It extends between almost 0 to about 4,000. So it's about 4 kilometers by 4 kilometers. I'm Canadian. I like to use metric. So it's going to be in kilometers. Or m meters, right? And then they'll give you a summary of the different variables that are now spatial features, which have their locations, and it'll tell you the summary statistics of them. And so we can look at that. We can also go ahead and do just a head on the coordinates of my data, and it'll confirm for us that in fact coordinates are the X and Y columns as we would expect. Now if we're going to do any type of variogram modeling, of course, we want to do a normal score transform of the data. Specifically, we plan to eventually use it within Gaussian simulation. We have to be consistent. We're working in Gaussian space. The variable should be first in Gaussian space. So we'll do a normal score transform. Now with R, all we have to do is do data frame $, and the name of the feature, and that gives us direct access to the feature, a one-dimensional vector of all of the values with that feature. And if we do that, we get out a npor.turn which TRN, which is going to be our transformed porosity. And it's going to include a bunch of different things. It's an object with a bunch of information about the transform. And it'll provide us like a lookup table and so forth. But what we want is the actual vector with the transform values. And so the member of that object that has that vector is known as nscore. So all we have to do is go $nscore. And with this command right here, we take our data frame, we append a brand new feature in it called nporosity for normal score porosity, and we copy in that vector, which has the right length to it. It is paired with the previous data values. It's in the same order, and so we just copy it right there, and that gives us all of the values with the normal score transform. And so we do that. We could always run that code, and we would find that we would get back. Now we have an additional feature, nscore porosity, nporosity. And so you could look through it very quickly and confirm that it makes sense. You could look at, okay, what's the largest value? Data point number 3 is the largest one in the n-score transform. You look at it, it's in fact 0.919, which is the largest value here. The lowest one is the first one. It indeed is the lowest value here. Remember, a normal score transform is a rank preserving transform. It makes sense. And so we'd expect these normal score transform values to have the same rank relative to each other. That's a quick little check to take that there hasn't been some scrambling of the data in this process. So you could do a summary. I like that. You can do a quick check on the summary statistics. And if you run that, you'll see, in fact, that you get the minimum, the first quartile, 25th percentile, the 50th percentile, the mean, the third quartile, which is the 75th percentile, and the maximum value. And now we can, of course, it's always a good idea to visualize your data. And so we can produce the histograms and the CDFs, porosity before transform, porosity after transform. And in fact, you can confirm that it's very Gaussian. It's got a beautiful bell-shaped curve. The S-curve for the CDF, we're in good shape. Now, you can't do any type of spatial modeling without visualization in space. We got to actually look spatially and see what's going on with the data. Now, so we're going to do that right now. Now, in order to do plotting and get a color scale, you have to specify the thresholds that you're going to use specifically for the color plotting. And so we specify that for porosity, but also we want to specify it for the case of the estimation or Kriging variance that we will visualize later. So these arrays here are just simply going to be the thresholds we use. And so let's go ahead and produce a bubble plot. Bubble plots are really quite straightforward. The size of the bubble is going to be based on the radius, or sometimes it can be the area of the bubble, depending on how you set it, will be based on the magnitude of the value that you're displaying. And they can be pretty useful to spot trends. I find I work better with color. And so we can go ahead and work with spatial point plot, and we can plot from our spatial point data frame the porosity values, and we can go ahead and specify specifically the axis, the scales, and so forth, the cutoffs that we want to use. And the result is we get a pretty good plot that we can see general type of behavior. We've got some high values here, kind of a mixed bag here, some low values in some other locations. So we see there appears to be pretty good spatial continuity. It doesn't jump too fast. There seems to be kind of highs beside highs, lows beside lows. It does look like there's short scale spatial continuity. Now, in order to model spatial continuity, we first need a positive definite spatial continuity model, a variogram model that's going to work in full 2 dimensions. The way to specify that model in the GStat package is we can do VGM, which says make a variogram model. It's going to have a Scilla 0.6. So that's the contribution of the first structure. The type of structure is exponential, EXP, SPH, GAU, could be used for Gaussian or for spherical. And then what we'll have is the range in the major direction. And this array right here, whenever we do C brackets, we're saying make an array. And this array simply has 2 parameters that are required to specify the full 2-dimensional geometric anisotropy model for this first contribution exponential, a 0.6 contribution. It says the azimuth of the major is 0.35. Oh, that way I guess. And it says the anisotropy ratio in the horizontal is 0.5. What does that mean? It means if 800 was the range in the major direction, azimuth 0.35, we would expect that in the 90-degree orthogonal direction, which would be 125, that we would have a range of 400. An anisotropy ratio 0.5, that's the ratio of the horizontal minor over the horizontal major. So it's half the size. And then negative 0.5. So we tell it to have a negative 0.4, I should say, which means that we're going to immediately have variability, or I should say we're immediately going to have uncertainty as we go away from the data. We would expect that Kriging would behave very smooth. It's going to approximate the mean or get close to the mean pretty quickly, result in a nice smooth map. So if we go ahead and we make that model and we look at the model, you'll see in fact that we have a single structure. We have a nugget that acts over all directions. It must. We know that from theory. Has no range parameters. We know that from theory. We have an exponential which has a contribution of 0.6, filling it out to the CIL of 1. Why CIL of 1? We're going to work with a Gaussian transform variable, which we anticipate will have a variance of 1 because we transformed it to be standard normal. And so we got our parameters for the directionality, for the horizontal anisotropy ratio, and the range in the major direction. So we presuppose the variogram model, but we still want to calculate the variogram models calculate the experimental variograms, I should say, in those directions from the available data set, plot it up, and just confirm that it's not a bad fit. We're not working with something contradictory with the data. We're not really focused on variogram modeling here, but it's a good idea. So what we do is, we'll make a name and color matrix so we can put labels on a legend with labels on our plot. We'll calculate the variogram in the two primary directions, the major direction 0.35, the minor direction 125, azimuth 125, and the variogram command is shown right here in order to make that calculation using the gstat package. You'll notice that we just specified that we're working with n porosity. That's the single data value or feature we're working with in space. We got the data frame. It's kind of funny here, but the methodology for calculating the variograms, you specify cutoff, and cutoff is the maximum distance over which you will calculate a variogram. Width is going to be the size of the bin. So in GeoLib standard geostatistical library talk, we would say that width is the lag distance, and we would say cutoff would be the number of lags times the lag's distance. So we're going to have 6 points calculated at 500, 1,000, 1,500, 2,000, 2,500, 3,000. Alpha is the azimuth of the primary direction, and tolerance horizontal is the horizontal azimuth tolerance. And so far so good. It's not too bad. They use a little bit different terminology in GStat, but if you're familiar with GS5, it's not too bad to get past it. This will give you variogram objects. Once you have the variogram objects, they include within them as members, dist will be the lag distance, gamma will be the variogram value. So we can use the plot command and simply plot our variograms. We can label the axis, make it look really nice, and so forth, and we're able to see what's going on. Another thing we'd want to do is we can take our variogram models that we've already defined, and we did that above, where we produced this anisotropic variogram model for porosity, and we'd want to project it in the primary directions, 0.35 and 1.25. The only trick to this is the fact that in GStat, in order to project it in a specific direction, you have to give it a unit vector in that direction. And this is going back to your basic trig, where you're able to say, okay, if I'm going 0.35, exactly what is that x and y in order to have a unit length of 1 in that direction. So I used a little bit of trig to calculate exactly what x and y would be, offset as negative or positive around the unit circle. Not a big deal. You can see the example here of how to do it. Pretty straightforward. You get the unit vector, and they'll give you the variogram model in those projections, and we just simply plot it as lines. If you look at it, this is the variogram right here. We got 35 degree azimuth, that's the major direction in blue. experimental blue points. The variogram model, it's got a 2-to-1 horizontal anisotropy ratio. So this would be twice the range as the minor, which is right here at 1, 2, 5. And it's in red with the red points. So we have that. Now what we want to do is build our grid that we can Krige or estimate on. And so we use our add chord function, which I included, just wrote it very simple to build a 2-dimensional spatial point data frame of all of the centroids of all of the cells that we want to estimate at. 400 by 400, we're going to have, what, 16,000 cells that we're estimating at. That's not too heavy lifting. Consider that many subsurface models are working with hundreds of millions of grid cells. So this isn't too bad. We built that. We're going to start with a little inverse distance just to get warmed up. And so we can go ahead and run the inverse distance program. In GStat, it's just IDW. And so we just specify what's the property that we're working with. Specifically, we got the power or weight that we want to use. And then we just specify what's the data frame, what the spatial point data frame we're working with, and what are the locations at which we're going to want to make those estimates. And so if we do that, we'll get out an object which is going to have all of our estimates available to us. If we look at it, we can say, well, what is it? What kind of object is this? So we do a class command on it. We'll find out, oh, it's a spatial point data frame. But it also includes some interesting things. It's going to include for us var1 PRED, which is going to be the predictions that are made at all points of those coordinates, the centroids of all of our cells, and we can go ahead and plot it. Now, just so that there's no surprises here, I've got a pretty powerful computer here. It's not great, but it's pretty new. If you run this command, you can see how fast it ran. It took about a second. To convert it to a spatial point data frame didn't take very long either. This is the part that takes a little bit of time, is plotting all of that data, 16,000 points, and looking at it. So it wasn't too bad. So what do we see here? Well, we see a inverse distance. Power is equal to 2. Can you see the data locations? Yes, you definitely can. They're really represented as points, and there's bullseyes around all the data. That's because with a power of 2, you're putting a pretty serious punishment on distance away from data, and so it creates a map that's very sensitive to distance. Now you can repeat that calculation for a power, inverse distance power equal 1, and if you do that, you get something like this. At the data locations, inverse distance will be an exact interpolator. It gives you an exactly the data values at the data locations. If you think about it, as distance goes to 0, power goes to, the weight goes to infinity, no matter what the power is. You'll put a little constant in there to avoid it from going to actual infinity, but the weight on data, the closest data, when you're basically at the data location, goes boom, like goes very high, and so you reproduce the data at the data locations. And so now if you change the inverse distance power weight to 3, look at what happens. This map becomes very locally changing. It's very locally sensitive. And so you can see these transitions and changes all over the place. It's pretty typical to use the power of 2. 3 is seen as being pretty extreme. 1 is seen as being just too general, too smooth, too like the average everywhere. Now let's do ordinary Kriging. We're here to do Kriging. Ordinary Kriging is the default within GStat. It's not a bad idea. We know our data set, we looked at it, has some non-stationarity. It'll give us a little bit of flexibility to cope with that. We don't have to fit a trend. Instead, we'll just rely on ordinary Kriging to locally find the mean. And so the Kriging command is shown right here. Once again, we just specify the property that we're working with. We can work with porosity from the spatial point data frame, my data. Chords are all of the locations we're trying to make estimates, defined as a spatial point data frame, once again, with X and Y. We have the model now. This is new. And this is set to the variogram model that we defined or built previously. And we're going to have some search parameters. Now, search parameters are important, as we discussed in the lecture, because Kriging is computationally expensive. You're going to have to invert an n by n matrix for every estimate. And in fact, with ordinary Kriging, it's n plus 1, because we have that additional sum of weights to 1 constraint. And so we want to limit the number of data locally in order to get a reasonable runtime. Now, I wasn't so concerned here because we only have 200 data in space, in this two-dimensional space. It didn't seem like it would be too bad to work with. And so what we find is that we could have limited it, but we left it pretty much wide open. We said, okay, what's the max dist? That's the maximum distance or search away from an unknown location to look for data. We said infinity, don't limit that. And min is going to be the minimum number of data that are included in order to make the estimate. We said just put it as 0. We're not worried about that because we're not even limiting the search. We're going to always have 200 data for every location. And O max is the number of data per octet. And in class we talked about the string effect. The effect of having too many data along a one-dimensional vector through your space can result in unusual weights to the edges, so the first and the last data. We're working in 2D. We're not worried about strings of data. We just say infinity here. We're not worried about it. Now just to get a sense of the runtime, if you run this, we didn't limit the search. So now it's going to be using 200 data for every single one of those locations, 16,000 different locations minus the data locations. You'll use the data at the data locations. And we go ahead and we get the run. It's done. It's created this new object porosity Kriging. Now we can visualize that. We can use the spatial point plot program again to visualize exactly what that looks like. And I can show you, if I run it, you'll get a sense of how long it takes. So once again, the plotting, a little bit of a bottleneck, but not terrible. It's not a very big model, though. I probably would be concerned if we were doing a couple of million cells or something. This would probably take quite a bit of time. But if we look at it, what does our Kriging look like? What are the general observations? First observation, you see the little hot pixels here that are a little bit different than their neighbors. Those are the data locations. There's some discontinuity away from the data. What causes that? Nugget effect. Because of the nugget effect, as soon as you go one cell away from the data, it says, well, I'm not very correlated with that data beside me, or I have some limited correlation with it. I'm going to be estimating with the local mean, and so it causes some jumps. What's the other thing we can notice? 2-to-1 horizontal anisotropy ratio in this direction, 0.35. Do you see it? The whole thing has this general kind of directionality imposed in it. Very, very interesting. Now, I told you in the lecture that Kriging is like a good friend. It will give you a pretty good estimate at each location. We'll say the best estimate as far as it minimizes the estimation variance. We'd call it the Kriging variance. But it also tells you how bad the estimates are. This is a map right here of the resulting Kriging variance, the estimation variance at every single location. What do you see here in general? Well, it's kind of interesting. First of all, you can see locations where it's low. Those are those darker colors. It doesn't go quite black because of the nugget effect, but it goes pretty low, down to probably around 0.4 because that would be where we start because the nugget effect is about 0.4 in this model. And so you can see where the data are. You can also see where the data are not. In the locations where it's yellow, you are really far away from the data at these points. And so you reach a point, in fact, if we're yellow, we're almost at the sill. We're almost at 1, which means that you know nothing. So if you get to the yellow here and you're actually getting to a Kriging variance equal to 1, that's a point at which you have no information. So, of course, when we're dealing with Kriging, we know that it does not reproduce the histogram. There's missing variance. It's too smooth. All of the estimates are just the best estimate in each location. It's never going to show you the max or the min value within the distribution. So to prove that, let's just produce a plot of the original porosity distribution. And then we have the Kriged porosity right here. And what you can see immediately is that, in fact, we get distribution that's much shrunk. The variance is shrunk, so we don't actually see the full variability anymore. And we'll talk about the smoothing effect of Kriging. Specifically, we'll get into the problem, to the solution, of working with Gaussian simulation as a way of returning the missing variance. Now, this is interesting. What if we had used search parameters that were poorly set? we were too restrictive in our search, so we didn't have enough data available. So we could set the maximum distance to 800, the maximum number of data per octant to just one data, and we can run Kriging and then plot it, and look what you get. It looks like something you could put on a t-shirt. That pattern is actually pretty cool. What's going on there? Why do you see all of the cuts and rays? What is that? It makes sense if you imagine a limited search, that you could have a very high value right here, and as you're moving away from it, suddenly that value is cut out because of the search parameter, but it's still pretty well correlated. And so that would dramatically shift the estimate as new data are being added and cut out while they're correlated. If we set the search as unlimited, data values will cut in and out in a slow manner as we're moving towards a data value. It becomes more and more correlated, more and more important, and then it starts becoming less important as we go past it. And so that makes sense. You have gentle type transitions, and your Kriging estimator will be, in the face of your data, much more smooth, much better behaved. So if you ever get something like this that looks like you should put it on a t-shirt with the name of your band or whatever, I don't know, a geostat band or something, you know that you have an issue with the search parameters. Open them up. Maybe go for lunch. If you've got a big model, it's going to take a while to run. If you have really kind of opened up search parameters, just go for lunch. Enjoy lunch. Maybe that's the day that you walk, you go beyond taco joint and you go someplace a little further away than off campus or what, depending where you are in the world. Okay, so we can do some experimentation. We'll make a variogram anisotropic again, but let's just get rid of that nugget effect nonsense. We don't want to use nugget effect anymore. And we'll run a porosity Krig with no nugget effect, and let's plot that up. Look at that. Nice, nice, nice. What's the difference? What's happened here? Well, let's go back to the one with nugget effect right here. Okay, look at that. See the data, discontinuous data. See the kind of general form of the model. It's not very much variation in the model. Go here and look at it. Without nugget effect, everything is better correlated to the local data. You have much more transitions and changes, and you have continuity at the data locations with the adjacent cells that are estimated. Really, really nice. Now, this is beautiful. Look at the Kriging variance with no nugget effect. Do you see the data? I see the data. All of those black circles are the locations where you have zero Kriging variance. That's the data locations. Bright, you can totally see them. You can see the locations where you have very poor information, but notice we never get to the SIL, we never get to the variance of 1 because everything is really well correlated. We have what? We have a range of about 400 and 800 in the major direction, if I remember right. So we have really good correlation over the whole model. You can even see the directionality. It's really quite nice here. Okay, so that's the end of the demonstration here of working with Kriging within the GStat plugin within R. Thank you very much to the author. Besma, I really enjoyed this package. It's pretty easy to work with. We'll see pretty quickly. It also does simulation and so forth. And so if you just need to get a little geostats done or experiment with it, it's nice to do in R. Of course, we can also do it in Python, Geostatistical Library, Pyrcz, GoCAD. A lot of methodologies for working with spatial models allows you to work with geostats and Kriging and simulation. All right, I hope that was helpful to you. If you have any questions, go ahead and fire me a question. My email is easily available. If you look up our department at University of Texas at Austin, Petroleum and Geosystems Engineering. But on Twitter, I'm Geostats Guy. You can always DM me there, drop me a message. Follow me if you want to learn more about ongoing research, other types of geostat resources, other lectures, and so forth. All right, I hope this was helpful.